Hello, everyone. Let's take a look at assignment 9 today. Assignment 9. I think I've decided that I would not go through the sort of conceptual underpinnings of FTC 1 and 2 again, and that we would just say if you wanted more on that, you could watch that video again, or read the textbook. Both are good sources of information on that. Look, my camera head seems to want to keep drifting. Why do you do that, camera head? Alright, so here we are talking about assignment 9. Let's start off with this bell word problem. The integral from 1 to 32 of x to the minus 6/5 dx. Please evaluate that integral. Hey, welcome back. So, did you think about finding the antiderivative here and using FTC 2 to evaluate the antiderivative? Well, the antiderivative of this, remember, I have to add 1 to that. So that's going to be x to the minus 1/5. Now, here's the thing. If I take the derivative of this, that's going to come down, and there's going to be a negative 1/5 here. There is no negative 1/5 here. So there must be something present in this initial function that when I take the derivative and bring that negative 1/5 down, there's canceling and it goes away. Okay? So what do I need so that when I bring down that negative 1/5, it cancels out? It's going to be negative 5. Oops, not up there, but down here. Negative 5. So if we bring this down, we've got negative 5 times negative 1/5. Yeah, they cancel. You remember your textbook talks about this as adding 1 up here, and then down here you're doing n plus 1, like this is n plus 1, and then that's n plus 1. So here we have a negative 1/5, and so here we would have a negative 1/5. But I'm not very keen on dividing by a fraction like that, so I flip and multiply. Don't forget the plus c. However, when we evaluate this antiderivative from 1 to 32, those c's are going to cancel out between those two evaluations. So remember, with definite integrals, you don't have to worry about the plus c, because they're always going to cancel out. It's the indefinite ones, the ones without boundaries, where you must have that plus c. So we've got negative 5 to 32 to the negative 1/5 minus negative 5, 1 to the negative 1/5. Okay, so negative 5. Oh, I can factor that out. Left with 1 over the 5th root of 32 minus 1 over the 5th root of 1. Yeah. Took that out. There's that minus. This goes on the bottom. This goes on the bottom. So it's going to be negative 5. 5th root of 32. Remember, 32 is 2 to the 5th, so those are going to cancel. And I'm going to have 1/2 minus 1. So negative 1/2 times negative 5 is positive 5/2. Okay? This, remember, we're using FTC 2. We're using the antiderivative here and here in order to evaluate this integral. Okay, how about this one? The integral from 0 to pi over 3 for secant x tan x dx. Give that one a try. Come back when you're done. Well, we remember secant tangent is not the derivative of tangent, nor is it the derivative of inverse secant, but it is the derivative of secant. So, and there's a constant. We've got 4 secant x from 0 to pi over 3. So it's going to be 4 secant pi over 3 minus secant 0. Remember, though, that this 4 has to be applied to each of these things. So secant of pi over 3, yeah, I don't know, but I do know cosine of pi over 3. Cosine of pi over 3 is 1/2. So secant of pi over 3 must be 2 over 1, because secant is the reciprocal of cosine. Secant of 0, well, that's 1 over cosine of 0. Cosine of 0 is 1, so 1 over 1 is 1. 2 minus 1 is 1 times 4, or 4. So the value of this integral is 4. Yes, you are expected to evaluate this. If you leave that like that, you will lose the answer point. Please make sure that you don't forget all your derivatives. Or even your trig evaluating skills from last year. All right, so now I'd like to find y prime if, here's the first one for you, y equals the integral from 0 to x of square root 1 minus t squared dt. Please find y prime. Come back when you're done. Welcome back. So this was a case where I was expecting you to take the derivative of both sides. And when we take the derivative of an integral, that's FTC 1. That's Fundamental Theorem of Calculus Part 1. So what did we say would happen? Derivative undoes integral, and this goes in here. 1 minus x squared. Don't forget the derivative of this with respect to x, but that's just 1. So there we go. No, there's no chain rule here because the derivative here is 1 to worry about. No, that's just a dummy variable. And if you're still not comfortable with that, you might want to go back and check out FTC Part 1 in video 8. All right, how about this one? Y equals the integral from x to the third to 4 of ln of t dt. Remember, we're trying to find y prime here. We're trying to find dy dx here. So pause your video, give it a try, come back when you're done. Did you realize that you can't do that yet until you flip these? Remember, we always need a constant here. And so now I'm ready to take the derivative. Y prime, that negative stays. The derivative here is going to be, well, derivative undoes integral. That goes in there. And then x to the third. Don't forget, though, you need to take the derivative of that. 3x squared. And don't lose that negative out in front that allows you to switch those bounds. Okay, one last one of these. How about in the case of y equals the integral from 3x to 2x to the third of 4 secant x tan x dx. Tell me about that one. It may take another minute or so for you to figure it out. Pause the video if you need more time. So I remember saying in video 8 that we were going to split this up into the integral from 0. Could be any constant. 3x to 0 of 4 secant x tan x dx plus the integral from 0 to 2x to the third for secant x tan x dx. Okay, remember, when we take a derivative, we need to have a constant down here. So with this one, I'm going to pull out that negative and flip my bounds. So what do we have? Well, we're supposed to recognize that secant tangent is the derivative of secant. So I have negative 4 secant x. Whoa! Yeah, I'm very sorry about this. We need our dummy variables. That other way goes to a very sad, sad place with all the points you've lost. So let me correct that. Okay. And so this is going to go in there, so we have a 3x. Don't forget, though, you need to take the derivative of that inner function there. So we're going to need 3. Notice how this goes here and here. Some students just put it in one of them. Don't put it in just one. Also, don't forget you need the derivative of that inside function. Okay, and then over here, no, we didn't put 0 in. Tangent of 0 minus -4 secant 0 tangent 0. Yeah, so that's evaluating here, and that's evaluating after this minus sign. Secant tangent. Took the derivative, plugged in the values. No. Let's start again. Okay. So here, and I think why I was having that difficulty was because I wasn't, in fact, explaining to my own brain what I was doing. And I'm taking the derivative at this step. So when I take the derivative of that integral, they cancel each other out, and this comes into those places. No, not that at all. Why not? Because the derivative of a constant is 0. So that second part that I was writing over here, yeah, no, that doesn't exist. Okay. So we've got dy dx equals -4 secant 3x tangent 3x. Don't forget the derivative of the inside function. Now we come over here. Plus, and we're taking the derivative of this stuff. We're going to have that 4 again. We're going to put the 2x to the third into each of those places. But don't forget we still need to have the derivative of that, which is going to be 6x. Yeah, I don't particularly see factoring that I can do except for the 4. So I'm probably not going to do any factoring. Ooh, and a 3. Still though, don't think I'm going to do any factoring there. Mostly, I just want to make sure you're comfortable with FTC 1 in those situations. Okay. What do we have left on our list to do? Oh, will you please evaluate this integral? The integral from 0 to 1, square root 1 minus t squared dt. Please evaluate that integral. So it sounds like many of you are trying to find the antiderivative of this. Problem is, yeah, you can't do that this way. It's not going to work. Yeah, just don't. Because look, you're going to say something like, hey, Mr. Yukla, what about, since this is 1 minus t squared to the 1/2, wouldn't it be 3/2 1 minus t squared? And I would say no. And then, other people, also very clever, would say, oh, yeah, there's that chain rule thing. So you need to have an over t squared, an over 2t, so that when you take the derivative of the inside, those two t's cancel. And it turns out no, because what we're looking at here is a quotient rule, and when I take the derivative of that quotient rule, I'm not going to get that. So how am I supposed to do this? Well, so here's the thing. In December, we first evaluated integrals by appealing to the geometry of the situation. And that's what I want you to do now. I want you to recognize this as a quarter circle. This is the equation of a semicircle, but we're only looking from 0 to 1. So we're looking for a quarter of a circle. The circle has a radius of 1. 1/4 pi 1 squared. Pi r squared is the area of the circle, and we only want a quarter of it. And so my integral is pi over 4. And yes, you do need to still know how to do that. All right, next, I'd like to look at this graph and use it for the next few problems. 1, 2, yes, yeah, 2, and then we're going down to 3, and we keep going down until we get to 4. Okay. And my units here are feet per second squared. And these are seconds. All right. And so my first question for you is find the integral from 0 to 4 of f of x dx. And this is a graph of f of x. Okay. So, how are we going to do this? That's right, we're going to appeal to the geometry of the situation here. It's exactly what we're going to do. So, I got triangle, triangle, triangle that goes downstairs. You know, if I'm just thinking about these areas, this one below the axis and this one above the axis, they're the same size. It's just one is going to be negative and one is going to be positive, so they cancel each other out. So all I really have is 1/2 base of 1. And what's my height? Oh, the height is 2. And here we'll have -2. So we've got 1/2, 1 times 2. That's the triangle. Plus this rectangle. Area of the rectangle is length, or base, times height. 2 minus 1 is 1, times the height of 2. And so I end up with 3. I can continue and say, oh look, I have this other one with a base of 1. 3 minus 2 is 1, times the height of 2. But then here, I've got 1/2 a base of 1. 4 minus 3 is 1. But what's the height? The height here is -2. And so these two triangles cancel each other out, leaving me just 1 plus 2 for 3. Okay? So the value of the integral is 3. Great. What about B? Find the average value of f on 0 to 4. Remember, when we're talking about average value, we're talking about an infinite number of heights of y values. And we want to know what the average of that infinite number of heights is. So, yes, of course, this doesn't say average rate of change, it says average value. I need to use the average value formula. Remember, average value is 1/b minus a, integral a to b of f of x dx. So just have to find the integral. Oh wait, we did already. And multiply by 1/b minus a. Our b value is 4, our a value is 0. And so that's going to be 4 minus 0 times 3. Right, times that integral. And that integral was 3. So 3/4. Okay, so that means the average of all these heights is somewhere here, 3/4, and here, 3/4. We're not asking you to find out when the function takes on that average value, but you should be able to do that as well, where you would set the equation of this line. Yes, they do expect you to write the equation of this line. You have 2 points. Set the equation of that line equal to 3/4 and solve for x. That's what we would expect there. But instead, what I want to know is, what does this mean? What can you tell me some units on this, for example? What am I looking at? What would be my units here on the 3? What would be my units here on the 3/4? Usually, when we can say what the units are, we can explain the meaning of this number in the context of the situation. So, what do you got? Well, here I know that when I integrate feet per second squared, I'm going to end up with feet per second. So, what's that mean? How do we get that? what am I doing here? What is this number? 3 feet per second. What does that represent? I know if I integrate velocity, I get a change in position. But here, I'm integrating feet per second squared. I'm integrating acceleration. And so what I'm getting is a change in velocity. Because this number is positive, velocity is increased by 3 feet per second over the interval from 0 to 4. Okay? So what about this number? What are its units? Well, these we just figured out were feet per second. And these things down here, these are seconds. So feet per second per second. Feet per second squared. So what this found for us, the average value of this function, since this function is acceleration, you found the average acceleration on that interval. Okay? Next, total area. Total area. What's the total area here? Well, we have that 1/2 base of 1, height of 2, plus that 1, height of 2, plus that 1/2 base of 1, height of 2, plus 1/2 base of 1, height of -2. Remember though, area is positive. And so I have to do that. So I've got 1, 2, 3 of the triangles plus the rectangle for a total area of 5. Okay? What would that represent? I don't know. Let's think about it. This, in essence, is flipping that up. Oops. So I've got something like that. I'm finding all this area, which means I'm doing feet per second times seconds. And so I think I'm looking at a change in speed. Change in speed. 5 feet per second change in speed is what I'm seeing here, I think. Well, I want to think about that some more. And while I'm thinking about that some more, here's a graph of part of cosine. Here's pi over 2, here's 0, 1, here's 3 pi over 2. And I, of course, want to find some things like 1, I want to find the integral from 0 to 3 pi over 2 of cosine x dx. And 2, I want to find the total area. Okay, give it a go. Pause the video. Come back when you're done. So straight integral, well, that's just, use the antiderivative. Use FTC 2, sine of x plus c, evaluated from 0 to 3 pi over 2. Since we have a definite integral, we don't need to worry about that. And so really I'm just looking at sine of 3 pi over 2 minus sine of 0. Well, sine of 3 pi over 2 is -1, sine of 0 is 0, and so I get -1. And I guess the way I can understand that is this area is equal to 1. All three of these are, but these cancel each other out. +1, -1, gone. This is the only one left. That's why I have a -1. Hey, so what about the total area? Well, 1, 1, 1, 3. How did I know that value was 1? Let's imagine I didn't know that value was 1. So let's integrate from 0 to pi over 2 cosine x dx. That's going to be sine of pi over 2 minus sine of 0. Sine of pi over 2 is 1, sine of 0 is 0, and I get 1. So this integral from 0 to pi over 2 has a value of 1. That's a 1, that's a 1, that's a 1. Since we want total area, and area is always positive, yeah. I mean, I could set this problem up like the integral from 0 to 3 pi over 2, absolute value, cosine x dx. But yeah, I don't know how to take antiderivative with absolute value symbols like that. I don't have a method for that. I could, and I often think that this is the way I prefer to do it, is to split this integral up. 0 to pi over 2 cosine x dx minus the integral from pi over 2 to 3 pi over 2 of cosine x dx. Why like that? Well, I want to subtract all this negative stuff, because when I subtract a negative, I'm going to end up with a positive. We just did this problem over here and found 1, and now when I do this, I'm going to have sine 3 pi over 2 minus sine pi over 2. Okay. Sine of 3 pi over 2, well, let's start over here. 1 minus. Sine of 3 pi over 2 is negative 1. Minus sine of pi over 2 is 1. So we're going to have minus 2 in the brackets. And 1 minus a minus 2 is 1 plus 2 or 3. This is the way I find most successful. Yeah. Most often, that is the best one if I only know one for me to be able to do. Let me get that. And how about total area? Okay. Total area. No, not integral. Graph. Sorry about that. So our first picture, it's pi over 2, and that's sine x. That's the line y equals 1. And I want to know what this area is. If we integrate from 0 to pi over 2 sine x dx, we're finding this stuff here. Yeah, I don't want that. I want this stuff here. And so, you know, we discussed a couple ways of doing that. One way is to find the area of this rectangle, pi over 2 times 1, or pi over 2, and subtract from that the area of the integral. So 1 times pi over 2 minus the integral from 0 to pi over 2 of sine x dx. Yeah, that's one approach to the problem. It's not the approach I prefer to take. Certainly works. What do we get here? Antiderivative of minus sine is positive cosine, and we're going from 0 to pi over 2. So cosine pi over 2 minus cosine 0. Cosine of pi over 2 is 0. Cosine of 0 is 1. So I've got pi over 2 now this met with that, so I have a plus 0 minus 1, or pi over 2 plus 0 minus 1, pi over 2 minus 1. All right, so that's this area here, pi over 2 minus 1. Hey, didn't we just realize that the area of one of these portions of cosine was equal to 1? It's true for sine too. All right, but that, like I said, isn't generally the way I do the problem. I think you're going to get a lot more traction if you think about this in terms when you see total area. Almost always the more efficient way to do this is to think about the integral of top minus bottom. Now, what am I talking about? Well, this is the function on top, and this is the function on the bottom. Why top minus bottom? Well, if I have a situation like this, where this was y equals 1, and this y value here was 1/2, and I would think about, hey, how long is that? Well, it's this number minus that number. That's 1/2. But what if down here the y value is 0, and then look, 1 minus 0 is 1. And over here, if I'm thinking about 3/4, I'm going to have, oh, sorry, the y value there is 3/4. I'm going to have this shorter distance, 1 minus 3/4, or 1/4. So really, top minus bottom is just finding the length of each of these segments. And then I'm adding them all up. So what's our top function? Well, it's this horizontal line, y equals 1, minus the bottom function, this sine x. So this is my integral from 0 to pi over 2. I don't need a bunch of pieces that I glue together. Instead, I'm just going to have one integral here. And so that's going to be the antiderivative of a constant, is that constant times b minus a. And then here, I want to know the antiderivative of minus sine. That's cosine. And I want to evaluate that from 0 to pi over 2. So over here, I'm getting 1 times pi over 2. And over here, cosine of pi over 2 is 0, minus cosine of 0 is 1. And again, I get pi over 2 minus 1. Same. In fact, you could come here and use your integral properties to split this up as two integrals. One of them would be the integral of the constant from 0 to pi over 2, and the other one would be the integral of the sine function, also from 0 to pi over 2. And isn't that the same as finding the area of the big rectangle? And there's finding the area under the sine curve, and so when we subtract them, we get this shaded area. So really, yeah, they all are kind of the same thing. Okay, so that was me walking you through one. Maybe you can walk me through this next one. How about this? Y equals x squared minus 1. And we've got a bunch of different regions here. Okay. That's 1, and that's 2, 3, and that's 0, -1. Okay, so let's call this region 1, and over here, region 2, and this part here, that part there, let's call that region 3. Well, I'd like to find each of these. Okay, pause the video, come back in a few minutes after you've given these a try. All right, well, I kind of actually want to start with R2 because R2 is just the area under this curve. So I'm going to integrate x squared minus 1 dx from 1 to 2. That means I'm going to use the antiderivative, x to the third over 3 minus x from 1 to 2. 2 to the third over 3 minus 2 minus 1 to the third minus 1. 1 to the third. Right, so that's going to be 8/3 minus 6/3 is 2/3 minus, and 1/3 minus 3/3 is -2/3. Minus a minus 2/3 is going to be 4/3. So this is just a straight integral to find the area of R2. Well, what about these others? How will I do R1? How will I do R3? Well, I think R1 is also the area between the curve and that x-axis. And so I think I'm looking at x squared minus 1 from 0 to 1. But because this integral is occurring below the x-axis, I expect a negative number to come from this. Let's see. X to the third over 3 minus x from 0 to 1. I'm getting 1/3 minus 1, minus 0 minus 0. And sure enough, I get negative 2/3. And that's cool. Now, some people actually have difficulty understanding where this is. Where this is, and you know what? Let me offer you an alternative. Instead of doing that straight integral, do top minus bottom. The top is y equals 0 minus bottom. The bottom is our parabola. Okay, top minus bottom. And I'm integrating from 0 to 1. So the integral of 0, that's just 0. It's the integral from 0 to 1 of negative x squared minus 1 dx. So what about this one? Well, when I think about this, I'm getting negative x to the third over 3. Minus a minus is plus x from 0 to 1. When I plug in my 1, I get 1/3 negative 1/3 plus 1. Because when I plug in zeros, these all go away. Or positive 2/3. Yeah, so top minus bottom was great, except I'm getting a positive 2/3, and this is below the x-axis. Oh, wait. The question was, what's the area of each region? So remember when we did this as the integral, and we integrated x squared minus 1 dx from 0 to 1, and we came up with negative 2/3. It's true the integral is negative 2/3, but since we were asked for area, we would have to turn this into positive. I wonder if people forget to do that on a regular basis. But look what happened over here when we did top minus bottom. Top minus bottom gave us that positive 2/3. So look, whenever you're doing an area problem, as opposed to just, integrate this, whenever you see that word area show up, I strongly encourage you to think about top minus bottom, or in some cases, right minus left. But we'll be seeing that later. For right now, no, just top minus bottom. Okay? All right. What am I doing for time? Yeah, we can move on. Can we move on? Oh, we didn't do R3. R3. So here's the thing about R3. Many students, when they do R3, here's that region. This is x squared minus 1. This is 1. This is 0, 0, 1, 0. Up here we have 2, 3. And here we have 0, 3. Is that true? Yeah. Okay, so how do I find this? Well, what happens is a lot of students do this. They do y equals 3. That's the top, minus x squared minus 1 dx. And they go from 0 to 2. And then I have to mark it wrong. How come? Isn't that top minus bottom? Well, yes and no. And mostly no here. The reason I'm going to say no is because I have two different bottoms. There are two different bottoms here. So yeah, I can definitely do top minus bottom. It's from 0 to 1. Top is 3, bottom is 0. Plus this integral from 1 to 2 of top minus bottom. Right. This is neither of these. This is trying to do the whole amount as though this was always the bottom function. And no, only from 1 to 2 is the blue parabola. the bottom function. Over here, now I got that horizontal thing. That's this going on. So 3 times 1 minus 0 is the value of that integral. And this one, I can do a bunch of different ways. You choose, doesn't matter to me. You might be the person who wants to go 1 to 2 of 3 minus x squared minus a minus 1 is plus 1. And say, hey, that's going to be 4 minus x squared from 1 to 2 dx. And then say, okay, 4, antiderivative of 4 is 4x. The antiderivative of x squared is x to the third over 3. And we're evaluating from 1 to 2. So that's going to be 8 minus 8 thirds minus 4 minus 1 third. So what are we going to get? 8 minus 4 is 4. Minus 8 thirds minus a minus 1 third or plus 1 third is minus 7 thirds. So it's going to be 12 thirds minus 7 thirds or 5 thirds. Don't forget over here you have this 3, which is 9 thirds plus 5 thirds, and I get 14 thirds here for my area. You could, of course, choose to split this integral up. Remember, we said that this part would be the integral from 1 to 2 of top minus bottom. And you could split that up into the integral from 1 to 2 of 3 dx minus the integral from 1 to 2 of x squared minus 1 dx. And don't forget that part there as well. All right, in fact, look at this. I guess I could even write this as the integral from 0 to 2 of 3 dx minus the integral from 1 to 2 of x squared minus 1 dx. And in essence, that's finding the area of the big rectangle and then taking away the area under our parabola. Well, that's cool. I like how, we can be thinking about all these different methods, and yet it turns out all of these different methods are in fact just rewritten versions of the same method. And that I find cool. All right. Ooh. So here I'm going to provide you with a function called f of x. And I'm going to have a straight line. And then we go up, and down, and down, and up. Okay, this is 5, 2. This is 3, 3, 2, 2, 1, 1. This here is 6. All right, so here we go. I need to tell you one more piece of information. That s of t, position, is the integral from 0 to t of f of x dx. Now, I'm going to say something that's going to be really hard for many of you to do, but I really, 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 really strongly encourage you to do this thing. And that is, don't ignore this piece of information. Really, force yourself to say, what am I looking at? Before I do any of these problems, and what kind of problems? These multi-part problems. We've got 6 parts to this problem. No, 7 parts to this problem. So if I don't understand what I'm looking at, it's likely I'm going to get most of those 7 wrong. Now, look what we say here. Position is the integral of this function. So the antiderivative of this is position. What must this be? This must be velocity. Okay? I'm looking at a velocity graph. I really need to establish that. And the only clue they gave me about it was this notation. Please don't ignore notation. It turns out to be so terribly important. All right? So, we're looking at a velocity graph. Let's take a look at the questions. Part A, velocity at t equals 5. Now, if I don't know this is a velocity graph, you know what most students say? They say, oh, I see an S. This must be a position graph. And they go here and they say, well, I know velocity is the slope or rate of change in position, and the slope here is 0, and they put 0. But we know that, in fact, position is the integral of this graph. Therefore, velocity is this graph. And if I want to know the velocity at 5, I just read the y value off the graph. There's the velocity at 5. B. What is A of 5 positive or negative? Well, let's think about that. Remember, acceleration is the derivative of velocity. Another word for derivative is slope. So if we take a look over here at 5, what can we say about the slope? Well, I think it's kind of 0. Neither would be my answer. A of 5 equals 0, because it looks to me like I have a slope of 0 there. Okay. B. Done. C. Find the position at t equals 3 if the initial position was 0. Okay, so they're telling me that s of 0 equals 0, and they want me to find s of 3. Where's this object at time equal to 3? Well, look up here. See how position has been defined as this integral from 0 to t? That means that I can say s of 3 minus s of 0 equals the integral from 0 to 3 of this graph of f of x dx. Okay, so let's find that integral. Oh, how convenient. A triangle whose height is 3 and whose base is 3. This is going to be 1/2 3 times 3 over here. And here, s of 0, well, we were told s of 0 was 0. And so it looks like s of 3 is simply going to be the area of that triangle. So when s of 0 is 0, s of 3 equals 3 times 3 is 9 halves. Now, how does this change? I don't know if you heard me, but when I finished reading the question, it said, find the position at t equals 3 if the initial position is 0, and then we have another one if the initial position is 10. So now they're telling us s of 0 equals 10. Well, how does that change our answer? S of 3 minus s of 0 equals the integral from 0 to 3 of this graph. Okay, s of 0, 10. Integral, well, it's the same triangle, so 1/2 3 times 3. And if I want s of 3 by itself, I better add 10 to both sides. So 9 halves plus 20 halves is 29 halves. Our position at 3 is very different depending on our initial condition. And I really want to point out this thing. This s of 3 minus s of 0 is the integral from 0 to 3 of this graph. Oh my God, we're going to be using this so often in Chapter 7. Please start using this. This FTC framework is so powerful and so successful in so many situations. You'll see me writing it a lot. Okay. Wish I hadn't done that because that's only half of the problems. D. So let's quickly draw it again. Boink. Up. Down. That spot. Down. And back up again. And that was 5, 2. And over here we have 3, 3. And yes, this is a straight line. That's why I knew this was 3 and this was 3. And how did I know it was a straight line? Because I saw the point 2, 2, and I saw the point 1, 1. And so really this is just y equals x. And that's how I knew that was a triangle. Okay, so let's take a look at D. D says, at what time during the first 9 seconds, I'm going to call that 9, at what time during the 9 seconds does S have the largest value? Well, isn't that interesting? So let's think about this. Let's think about this a couple of ways. S is largest. Well, this is not a graph of S. This is a graph of F, and we're told that S is actually the integral of f of t to t. Or I guess these were x's and this is a t. So I know I'm looking at a velocity graph here. So how is that going to help me figure out when S is largest? Well, let's think about this. Over here, S equals the integral from 0 to t of this graph. And integral means area under the curve. Okay. Bigger, 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 bigger. S is getting bigger and bigger and bigger because we keep adding more and more area to the amount that we have. What happens after 6? Well, these are negatives now. And these negatives are going to start nibbling away at all the positiveness that I had over here. And by the time I get over here to 9, I've nibbled away at a whole bunch. So now I have much less than I had at 6. So, yeah, I think 6. All right. Yeah, I know. I can hear you saying, well, how am I supposed to write that up? Yeah, how about this? Let's think about this problem this way. I know that if I want S to be largest, that reminds me a lot of the stuff we were doing in November when we were talking about maxes and mins. If I want S to be largest, that's when...
Cascades.
Sorry, gotta take this call. Hello. Hello. Did you go away? They went away. Okay, they went away. I guess I'm not pausing the video. So, look, if I want S to be largest, we learned in optimization that we want to look at the derivative of S. And we want to find out when S prime is 0, undefined, or endpoints. Okay, so what's S prime? Well, S prime is also called V. So I'm looking for when V equals 0 at this endpoint, and here. And so if I'm looking at V equals S prime, and I've got 6 here, I see V is positive and then V is negative, and so I know that my max occurs here at t equal to 6. Well, I like that a lot. Yeah, that's very nice. So I would encourage you to be comfortable, of course, with both of those ideas, but not necessarily. You can still make do with any one of them. Okay, same situation, but now we're asking the question in part E, when is A of t equal to 0? We want to know when A of t equals 0. Well, remember that A of t is the same as V prime of t, or the slopes on the given graph. And so it looked to me, when we were looking at this graph, that we had 3 places. One of them was here, and that was about 4. There was another one over here in negative land. Whoa! Stop drifting. There was another one over here in negative land, and there was also this one here. If this is 6 and I had 9 over there, let's call that one 7, and let's call that one 5. 3 places where I had a horizontal tangent, 3 places where the slope on this graph would be 0. And so a of t is equal to 0 at t equals 4, 5, and 7. Okay. When is the object moving toward the origin? When are we moving away from the origin? That's interesting. So if I look at this graph, here's my graph. This is f, also known surreptitiously as v. Positive velocity, moving to the right, I'm moving to the right, I'm moving to the right, I'm moving to the right. I stop moving. Velocity equals 0. And I turn around and I start moving to the left, moving to the left, moving to the left. And so what was happening here? Well, I was starting someplace and, let's say s of 0 equals 0. And I'm moving to the right, moving to the right, moving to the right, moving to the right. So this is me moving to the right for those first 6 seconds. Okay, move away from the origin. And the origin isn't this place here. The origin is this place here on the position graph at t equals 0. Okay, so I'm moving away from the origin from 0 to 6 and moving back toward. Look, now we've stopped and we start moving to the left, moving to the left, moving to the left. Does our amount of motion to the left overcome all the motion to the right? Have we gone past the origin? No. I'm starting at the origin and moving all this area to the right. Yeah, I've moved back to the left. I've moved closer. I've moved toward the origin on 6 to 9. Yeah. Now, if this area were smaller than this area, 9, then I would say, hey, look, I moved a whole lot more to the left than I had moved to the right. And so here, if I'm starting at the origin, once I've overcome all that positive area, like by here, that would be me getting back to the origin. And now I'm moving away from the origin again, but this time moving to the left of the origin. Wow, there was some thinking there. Okay, and was there another part? On which side of the origin are we at t equals 9? Well, I think we kind of answered that. We noticed here in our graph that the amount we moved to the left was much smaller than the amount we moved to the right, and therefore we are still to the right of the origin. We haven't overcome things. I wonder what would happen if we changed this. But we're going to wait for that another day. And I'm going to say, I hope this was helpful, and I look forward to taking any questions you have. All right, take care, everyone.